Hello friends, welcome to Edupedia World. In this tutorial, we are going to learn about concurrency control part 5. So in part 5 of currency control, we are going to cover the following topics. We are going to see what is volatile keyword, then we'll see reentrance lockout, then we'll study about semaphores, blocking queues, and finally thread pools. Now let's begin. So first of all, what is volatile keyword? Well, in general, each thread has its own copy of variable such that one thread is not concerned with the values of same variable in other thread. But sometimes this may not be the case. Consider a scenario in which count variable is holding the number of times method is called for a given class, irrespective of any calling thread. In this case, irrespective of thread access, the count has to be increased. In this case, the count variable is declared as volatile. The copy of volatile variable is stored in the main memory. So every time a thread accesses the variable, even for reading purpose, the local copy is updated each time from the main memory. Volatile variable also have performance issue. Now let's do a quick small example of volatile keyword and let's see how does it operate with the threads. Okay guys, so this is an example of a simple thread where we are creating two threads T and T2 and we are passing a new object of myRunnable. So every time we are creating a new instance of this class and creating thread by passing as a parameter in the thread constructor. And after that, we are calling the run method for both the threads we have created. Fine. So this is thread. Now let's see how volatile is used. Now just let me create, first of all, count variable. Okay. And every time run is called, let me increment the count. Fine. So I'm using pre-increment operator to increment the count. And once that is done, let me also print the count over here. So I'm printing count is okay. Now let's run this code. So you see every time it's printing the thread name and it's printing the count as 1. Okay, but what I wanted to do is I want to actually check how many times the run is called or how many times this thread that we are executing is calling the run method. So no matter irrespective of the thread, let's say if I have created 10 threads and each of them is calling run method once, then my count should come as 10. Okay. And if I'm creating 100 threads and each of them is calling run method once, then my count should come as 100. Okay. How do I do that? Since over here count is a local variable and it is related to the object of class myRunnable. So every object of class myRunnable will have a different count variable. Fine. But now let's say I want to create this count so that it gives me the value that will give me how many times the run is called. Fine. So what if I change it to volatile? Will it do any impact on this? Or will our output be anyhow different if I do this? Well, let's see that. So up till now you see it is still 1. Okay. Now let me do another thing and change it to static. Fine. If I do that, then you see my count variable is incremented to 2. Why so? Because first time when my count is called, it was 0, right? Over here, let me just initialize it to 0. Okay. And it was incremented to 1. But before this increment happens, my other thread also incremented the same count variable. After that, both the threads printed this line which was 2. Now, in order to print it one by one, let me use synchronized keyword over here. Okay guys, here I have changed the implementation a little bit. So over here you can see I have created a single myRunnable object R, and I'm passing the same object to both the threads. And then I have created a static volatile data member, that is int count, and given the value as 0. Then inside a run I'm calling another method add. Instead of creating a synchronized block, I'm creating a synchronized add method where I'm doing printing the thread name before, then incrementing the count, again printing the thread name, and then printing the thread name and count. Okay, so let's run this example. Now if I run this, you see first of all thread 0 did all the work inside the add method. So it printed the name of thread twice and then printed the name of thread with count. That was 1. Okay. So since count is static and volatile variable, so therefore being static, the value will remain common. Okay. Then we have int count equals to 0. So if I do, count equals to 0, then it will make sure that the count which was 1 is got incremented to, that was incremented to 1, now will be incremented to 2 since it's a static variable. And volatile is making sure that always the latest copy is picked up. So over here you can see I have used two keywords. One is volatile and other is synchronized. So your volatile actually guarantees only visibility. That means the latest value of the variable count will be visible to each and every thread. Whereas synchronized keyword guarantees visibility and atomicity. That means all the operation inside it will be, completed once and the latest value will be visible to the other thread. Okay. So, its synchronization is used for a different purpose. Your atomicity doesn't matter, then you can remove your synchronized variable, and after, add is called on both the variable, you can simply try printing out over here your count variable. So if you will print a count variable using volatile keyword, you will see that every time the thread will reach the latest value of the count. So no matter, like, although there are two threads and if one thread has already updated the value, then the second thread will always read the updated value. Since I haven't used synchronize, so the sequence how they are done, it's not there, and how they're printing, it's not there. But see the latest, I mean the value that is printed over here is 2, and another one is 1 that was printed by previous. So once the value got incremented to 1, it again got incremented to 2, then our previous thread, or the thread which incremented it to 2 actually prints this line to 2 and then 1. So if I just run it again, you see it's giving me 2 and 2. So the thing is, your volatile ensure that your thread actually reads the latest value. If I just remove volatile, the guarantee is not there. It might occur that, the latest value is picked up by the thread, but it also might occur that it is not picked up. So there is no guarantee that always the latest value will be picked up. It might happen that it has, one thread is changing in the meanwhile, other thread also start reading one and it's not, the latest value is not picked up. So there could be chances. So that is the purpose of volatile over here. Let's go back to our tutorial. Okay, so the next topic is Reentrance Lockout. Well, Reentrance Lockout is a situation similar to deadlock and nested monitor lockout. Reentrance Lockout is also covered in part of the text where we already studied locks and read-write locks. Okay, so let's see what is lockout situation of reentrance lock. Okay. It may occur if thread re-enters a lock, that is read-write lock or some other synchronizer. There is no re-entrant. Re-entrant means that thread has already holds a lock, can retake it. Java synchronized block are re-entrant. Therefore, the following code will work without problem. Public class reentrant, and then we have public synchronized outer, which is calling inner, and then in inner we are doing again something which is a synchronized method. Now notice how both outer and inner are declared synchronized, which in Java is equivalent to synchronized block. If the thread calls outer, there is no problem calling inner from inside outer. Since both methods are synchronized on same monitor object, if a thread already holds a lock on monitor object, it has access to all blocks synchronized on the same monitor object. This is called reentrance. The thread can re-enter any block of code for which it already holds the lock. The following implementation is not reentrant, so you see over here we are just having a is logged, and once a thread enters this implementation, and if again a thread tries to get a lock on the same variable, it won't be able to do so. We have already seen this kind of implementation in our previous tutorial. Now, if a thread calls lock twice without calling unlock in between, the second call to lock will block. A reentrance lockout has occurred. To avoid reentrance lockout, you have two options. That is, avoid writing code that reenters lock, or otherwise use reentrant lock. And what is reentrant lock? We have already studied. Next important topic we are going to cover is semaphores. Well, if we talk about semaphore, a semaphore is a thread synchronization construct that can be used either to send signals between threads or to avoid missed signals, or to guard the critical section like you would do with a lock. Fine, so this is about semaphore. So it is also, you can say, a kind of locking mechanism, and it's like really effective locking mechanism. Java 5 comes with semaphore implementation in java.util.concurrent package. So you don't have to implement your own semaphore. Still, it can be useful. Still, you can use it because we are having its own implementation. Fine. Okay, now we have, here is a simple semaphore implementation where we are having a private class semaphore and using a Boolean signal false in it. Fine. After that, we are having synchronized method which is take. It is actually making the signal to true and calling notify. Then we are having synchronized release, which is throwing interrupted exception. What it is doing is it is calling wait while this dot signal is false, and it is making this dot signals to false. Fine. So I hope so you got what I'm trying to say. So it's a kind of internally using wait and notify, but it is also using a signal which is true and false. Whenever it changes it to wait, even if it's not, then whenever release is called, the signal is turned to false. That means the lock is not there. Whenever it does take, then it makes to true, and it also notifies other waiting objects. The take method would send a signal which is stored internally in semaphore. The release method waits for the signal. When received, a signal flag is cleared again, the release method exited. So whenever we actually clear the flag again, the release method actually exit. Using a semaphore like this, you can avoid missed signals. You will take instead notify, So you will call take, and instead of notify, instead of directly calling notify, you will call take, okay, and release instead of wait. If the call to take happens before you call release, okay, the thread calling release will still know that take was called, because the signal is stored internally in the signal variable. Okay, so even if you call release when before calling take, it will still get to know because signal value will change. The names take and release may seem bit odd when using semaphore signaling. The names origin from the use of semaphore as lock. Okay. So this is using semaphore for signal. So this is, whenever we need to signal, then we use semaphore. Okay, so you see over here, we have created an object of a semaphore class, and the object name is semaphore. Then we are sending the thread sender. So sending thread is our class and the object is sender. Similarly, we are having another class receiving thread and receiver. So on both of these things, we are sending the same semaphore object, and then we are calling or starting both of the threads by calling start method. So when we do that, you see we are sending a semaphore and each of them in their constructor is setting the semaphore object that they are having in their class. Okay. In the run method, so while true, it does something whatever it wants to do, and then it calls semaphore take method. Okay. Similarly, in receiving thread inside the run, it calls semaphore release method. So in this case, you see we are using a same semaphore object for signaling whenever sending thread is completed, it has done its job, and the receiving thread has also done its job. They can signal to each other. So when we call like the take method, so the take method of semaphore, as we have seen previously, it signifies notify, and whenever a release method is there, notifies wait. So whenever receiver just starts, it actually sends wait signal. So the wait signal is over here, like while this dot signal, while not this dot signal, then it will call for wait, and it will change signal equals to false, and it will change signal equals to true, and it will call notify. So this is how this happens. Receiving signals actually releases the lock and sending signals actually take the lock. So this is how we use semaphore for signaling. Then we have counting semaphore, where this is, you can say, a very well used or very well practiced semaphore techniques, and it is used in many applications. So this is an important topic. It says semaphore implementation in previous section does not count number of signals sent to it by take method calls. We can change the semaphore to do so. This is called counting semaphore. Here is the implementation. So it is exactly same as normal semaphore, but it is also counting the signal. So it is having a private int signal equals to 0. And whenever there is a take signal happens, it increment the signal counter, and whenever release happens, it decrements the signal counter. So this is how the counting semaphore keeps the count of the number of blocks being acquired. Then we are having the bounded semaphore. Well, counting semaphore has no upper bound on how many signals it can store. We can change the semaphore implementation to have an upper bound like this. So whenever you want to, give a upper bound, that is the maximum limit of locks can be obtained, you can do that by using bound. Okay. Notice how the take method now blocks the number of signal is equal to upper bound. So there is a condition in the take method which check the number of signals. If it's equals to upper bound, okay, then we keep on calling the wait. Otherwise, when that is done, after the wait, it will increment the signals and it will call the notify. Then in release, we are again having like this decrement of signals, and it will checking for the signal being 0. Okay. Now using semaphores as lock. It is possible to use a bounded semaphore as a lock. To do so, set the upper bound to 1 and have a call to take and release guard the critical section. Here is an example. So you see over here we are having a bounded semaphore, and the new bounded semaphore we are giving the bound as 1. So that means only 1 can be take or release will work over here. So when we do semaphore dot take and then we go to a critical section, once that is done, finally we are doing semaphore dot release. Okay. In contrast to signaling use case, the method take and release are now called by the same thread. Since only one thread is allowed to take the semaphore, all other threads calling take will be blocked until release is called. Okay, the call to release will never block since there has always been a call to take first. You can always use bounded semaphore to limit the number of threads allowed in the section of code. For instance, in above example, and if you set the bound semaphore limit to 5, well, it will allow 5 thread and 5 thread will be allowed to enter the critical section at the same time. You would have to make sure though that the thread operation do not conflict, or you should write only that thing which should not conflict inside the critical section. Okay. Then we are having release method is called from inside the finary block to make sure that it is called even if the exception is thrown in from the critical section. Fine. So guys, then we cover a topic known as blocking queue. Well, blocking queue is a queue that blocks when you try to dequeue from it and queue is empty. So, it's kind of a queue. So, whenever there is a thread which wants to take a lock, it goes into the blocking queue, and whenever a lock is available from that blocking queue, we are, asking a thread to leave the queue and acquire a lock. Okay. So basically what happens is a blocking queue is a queue that blocks when you try to dequeue from it and queue is empty. Or if you try to enqueue the items to it, the queue is already full. The thread trying to dequeue from an empty queue is blocked until some threads insert an item into the queue. A thread trying to enqueue an item in a full queue is blocked until some other thread makes space in the queue, either by dequeuing one or more items or clearing the queue completely. So it is a kind of queue that ensures that, okay, this is a queue of the thread that can take the lock, and if you want to insert the queue and the queue is filled, then you have to take out some of the object. Java 5 comes with blocking queue implementation in java.ut.concurrent package, and the class known as is blocking queue. So this is the implementation of blocking queue. You can see we are having a queue, linked list queue, and the limit we set is to 10. So there are 10 objects that can be kept in this blocking queue. Okay, then inside the blocking queue constructor, we are taking the limit, and since already we have defined 10, but if user want to increase and decrease the limit, so there is a constructor to do that. And then we have two methods, which is enqueue and dequeue. In enqueue method, which is a synchronized method, we are checking the queue size. If it has reached the limit, then we ask it to wait. Okay, then the currently executing thread will need to wait for the other thread to complete. So when it's doing wait, that means it will just wait for the queue to get empty. Meanwhile, let's say in the dequeue, it checks if the queue size is 0. If it's 0, then nothing to take out of the queue, then again it's wait. And suppose if it's not 0, if it's if this queue dot size is equal to this limit, then that means it is reached at the full, and it will notify all that its task is done. So now other people can take its job is done. Now other people can take the things. Okay. So if the queue size is equals to limit, then the dequeue will notify all. So once notify all happens, wait over here, if you see if this dot queue dot size is equal to 0, then it is doing notify all. In that case, this dot queue dot add item will happen, and in this case it will return by removing a item. So this is how bounded semaphore blocking queue work. And now let's see thread pools. Well, just before going to a thread pool, I would like to pause over here since I don't want to stretch this video too long, and I will cover thread pool probably in the next section. Okay guys, so thank you very much. Let's meet in the next tutorial.